All right, welcome back. Here we are on our last leg of our nephron journey here. We're going to take a look at the distal convoluted tubule and collecting duct. Simultaneously, they have some very similar processes and things that they reabsorb and secrete as the tubular fluid is making its way down towards the end of the line here. So again, here's our overview picture. We have successfully, hopefully, gone over the filtration of the at the glomerulus, picking up with the filtrate at the glomerular capsule. We went through the reabsorption, mostly of water, organic molecules, sodium, bicarb, some secretion of hydrogen ions at the PCT. We took a look at countercurrent multiplication and the primary reabsorption of sodium and chloride in water of the nephron loop. And now we're going to take a look at this last piece here, the distal convoluted tubule and the collecting duct. All right, so let's get going. All right, so here we are again taking a look at some of these simple cuboidal cells that we found lining the distal convoluted tubule and the collecting duct. And you just want to keep note here of the diagram. So this first diagram is just taking a look at what's happening in the distal convoluted tubule, where these last two are both what's happening on the DCT and collecting duct. So that's why I kind of comboed these together, because they're most of their activities are going to be the same on both the collecting duct and the distal convoluted tubule. So the first little kind of strip here, this column that we're going to be taking a look at, is the reabsorption of salts. So here we see some countertransport. Again, there's more sodium and chloride that's coming in from the tubular fluid. We have our countertransport reabsorption of chloride ions and sodium ions. We can see a leak channel for the reabsorption of sodium. We can see our active transport sodium-potassium pump bringing sodium in, and we see some secretion of potassium through this little leak channel. So again, if we're going to be keeping track, I'll just write DCT over here. DCT, what we reabsorb, I'll abbreviate that. So if we take a look at what we see ending up in the bloodstream, we have sodium and chlorine. All right, so that's what's happening. And then as far as secretion goes, so far we have potassium. So that's our first little strip that's happening just at the distal convoluted tubule. In this middle slice here, what we're seeing is specific to a situation with aldosterone regulated reabsorption. So now I got to go back to endocrine and blood pressure regulation. And what was the job of aldosterone? So remember, aldosterone was secreted from the adrenal cortex. Its role was to increase the reabsorption of water, and it did that by reabsorbing sodium at the release of potassium. So these little yellow circles with the A's in them represent an increase of these sodium-potassium pumps. They're aldosterone sensitive sodium-potassium pumps. So whenever aldosterone shows up to these simple cuboidal epitheliums, it binds the receptor triggers this transduction of a message to say, hey, we need to put up more sodium-potassium pumps on the surface. And so what we end up getting is the reabsorption of sodium, the secretion of potassium, and what's not shown here, anybody want to take a guess? Water. Water is going to be following that solute. So we are going to be reabsorbing sodium, and now we can add over here water. And potassium is still in our secretion column over there. So this middle slice here, this part B, is just showing you that the cells of the distal convoluted tubule and collecting duct are sensitive to aldosterone. So whenever we talk about aldosterone increasing water retention, this is where that hormone goes to do its action. It triggers the reabsorption of sodium, kicking out potassium. Water follows the concentration of sodium into the bloodstream. And so we are indirectly reabsorbing water by directly actively pumping sodium back into our blood. Okay, the last panel here is the most complex, right? We got to save the best for last. So this is again what's happening along the distal convoluted tubule and the collecting duct and the entire length of both of those things. So this is focusing primarily on hydrogen ions and bicarb. So you know you've got a little bit of experience of that with the respiratory system, a tiny little bit in the parietal cells with the digestive system, and so here we're seeing it again in the urinary system. So when we talk about, and then in the chapter 27, you'll be seeing the acid-base balance. Hydrogen and bicarb really drive your blood's regulation, blood pH regulation. So typically, we are acidic beings. We have to come up with ways to buffer all of these excess hydrogen ions that are being produced in our blood. So the kidneys do a really important job of regulating that. They have a really good ability to reabsorb and actually generate bicarb ions, and they have a really good way to get rid of excess hydrogen. So that's what we're going to look at here in this typical state in which we would have excess hydrogen ions that we want to get rid of. But I'll talk about alternative states as well. Say we're an alkaline state as opposed to an acidic state. So I'll put my collecting duct over here so we can keep track of what is reabsorbed and what is secreted. Okay, running out of space, but we'll fit it all in. Okay. So first thing, let's take a look at, kind of moving from the left to the right, we're going to take a look at carbon dioxide. So we do have carbon dioxide in their filtrate. We saw that back in the PCT. So as the carbon dioxide is diffusing in, kind of right here, we can see, hey, look at that. There's that equation again, carbonic acid bicarbonate buffer equation. That is going to mix with the water that's already in the cytoplasm of the tubular cell. It will generate bicarb and hydrogen. Right? So those are the two products. We should be very comfortable with that. So we've just created bicarb, which is great. So here we are going to reabsorb our bicarb with this counter transport. Hey, look, it's chlorine. It's like the chloride shift alkaline tide mechanism all over again, but just now implanted in these cells. So we're going to be reabsorbing bicarb. So I can go over and add that to my list. Oops. Squeeze it over here, HCO3 minus. All right, so we are reabsorbing bicarb at the distal convoluted tubule and the collecting duct, right? So now, where's the other half of that product go? So the hydrogen ions, if we take a look at that, the hydrogen ions get counter-transported with sodium. So we are going to actively pump, so it's an exchange pump. We're going to pump hydrogen ions out. So we are going to secrete hydrogen ions in both places. All right, so we're keeping track of everything. We can also see some of this chloride that we are moving in can also be secreted out as, and then when it goes into the tubular fluid, it will make hydrochloric acid, very much like we saw in the parietal cell in the stomach gastric glands. So we will secrete chloride. Okay. Now take a look with a hydrogen counter exchange pump. We are bringing in some sodium, and we do a counter exchange pump with hydrogen. So we are also secreting more hydrogen. So we can bring in sodium. I already have sodium listed over here in my DCT, but I can add it now to my collecting duct. All right. And so then we are moving down, from left to right, moving over. So here we have this new process. We haven't seen this before. You might see it saw it in chapter 25 with the take-home assignment, is we have the ability in our cells, all over, but not just these ones, but all over, the ability to convert amino acids into different organic molecules. And the main way that they do that, first off, is you have to remove that amine group, or amino acid. It's an amine on one side, carboxylic acid on the other. When we remove that amine group, we now have just a carbon and hydrogen and oxygen molecule, which can be converted into almost anything. In this case, it can be converted into bicarbonate ion. So this is bicarbonate ion generation from amino acids. So we can then reabsorb the bicarb while kicking out some chlorine. The ammonia is a waste product. So the ammonia with some chlorine becomes ammonium chloride, which is kind of like a base. It almost acts like a buffer. The ammonium chloride and the hydrochloric acid kind of neutralize themselves out. So we can secrete ammonia, NH4+. Okay, that's supposed to be a plus. I'm writing really small, NH4+. So we are getting rid of ammonia ions, ammonium ions. We are reabsorbing bicarb and sodium in the collecting duct, as well as chlorine ions, sodium ions in the distal convoluted tubule as well. So I'm looking at my list. Yes, I think I've covered everything. And so this is the typical scene that you would see in the collecting duct in the distal convoluted tubule. Is we are actively trying to reabsorb bicarb, with actively trying to reabsorb sodium and chloride, and kicking out hydrogen ions. However, please know, I'm going to put this, I'll put it in purple because purple is kind of halfway between red and blue, is please know that we have the ability, as needed, to swap the reabsorption of bicarb and hydrogen ions to maintain blood pH. So we're going to see that in chapter 27. This is the typical way we're going to see it here pictured, that we're reabsorbing bicarb and kicking off hydrogen. But if your blood is alkaline, if it has too much bicarb, the kidneys can reverse these mechanisms, and we can hold on to hydrogen ion and kick out bicarb as we need it. So I wrote those in purple because that reabsorption secretion of those things in the purple are dependent on the blood pH. Okay. All right, so let's take a look this final slide of the effects of ADH on the distal convoluted tubule and collecting duct. We just saw what aldosterone does. If you remember, aldosterone helped to increase water retention. If you can remember ADH, anti-diuretic hormone, we saw that again way back in endocrine. We saw it again in the blood pressure chapter. Anti-diuretic prevents you from urinating, right? The target tissues for ADH was your renal tubules, your kidney tubules. So it is the cells of your DCT and collecting duct that the ADH targets and increases the aquaporins. So you're going to open up those membranes to allow water to be reabsorbed into the bloodstream. So let's say you have little ADH right here, or no ADH. So if you don't have any ADH, the only water reabsorption you're going to get happening is at the PCT and your nephron loop. You're not getting any water reabsorption at the distal convoluted tubule or the collecting duct. So what you end up producing is large volumes of very dilute urine. It's the same amount of solute that you may have been excreting, but now that same amount of solute is diluted in huge volumes of water, and you're going to get large volumes of dilute urine. So anything that blocks ADH, like alcoholic beverages, blocks your release of ADH from your pituitary gland. So that's why you pee a lot after drinking alcohol. Not that you're just drinking fluids, which could be a part of it, but it's basically telling your kidneys stop reabsorbing water. And so you just flush out a ton of water from your kidneys because it's not allowing you to hold on to that. Now, in the presence of ADH, what we see is these aquaporins are going to go and start kind of placing themselves in the membrane of the DCT and the collecting duct. And because we have this hypertonic, right, if you remember, this is our hypertonic environment all the way from 900, 600, 900, 1200 milliosmoles outside of the tube. When you open up those aquaporins due to the presence of the ADH, we're going to reabsorb a lot of water. And what you end up with is small volumes of very concentrated urine. So this is what you would get if you are dehydrated or you haven't drinking water in a long time. Your brain is recognizing that your ions are getting too concentrated. We need to hold on to more water. It makes you thirsty. If you can drink more water, that's great, but it tells your kidneys to hold on to the water, reclaim that water, put it back into the peritubular capillaries, and just excrete the smallest amount that you can with all the solids you would have secreted before, but it's in a less amount of water. All right, so that is our function of, or the effects of ADH, anti-diuretic hormone, on your collecting duct and your distal convoluted tubule. And I think that pretty much wraps up our journey. We made it all the way from filtration at the glomerulus to urine out of the collecting duct. There's gonna be one more video, I think one more, taking a look at the summary. I'm gonna put it all on one slide, and then the reflexive micturition of urination will wrap us up for chapter 26. Yeah, okay. See you next time.